June 3rd, 1980, 02:47 hours Mountain Time, North American Aerospace Defense Command Operations Center, Cheyenne Mountain Complex, Colorado Springs, Colorado. Captain Richard Krisiak, Senior Controller at Console 1, watched his primary display screen transition from its normal green tactical map, showing routine air traffic over North America, to a cluster of red icons appearing off the Atlantic coast. The first icon appeared at 24714. Designated Contact Sierra 1, the icon represented a detected ballistic missile launch from a Soviet submarine operating in the Atlantic Ocean. The icon was red, indicating hostile launch. The computer displayed trajectory data, submarine-launched ballistic missile, projected impact point somewhere on the eastern seaboard, estimated time to impact, 18 minutes. At 0247.18, 4 seconds later, another icon appeared. Contact Sierra 2, another SLBM launch, then another. Within 15 seconds, Krisiak's screen showed 27 red icons, all representing Soviet submarine-launched ballistic missiles inbound toward the United States. The computer-generated voice announcement system activated. Warning, missile launch detected. Warning, missile launch detected. The mechanical voice repeated every 3 seconds, creating an audio backdrop of urgent, emotionless warning that filled the operations center. Krisiak had been on duty at NORAD for 4 years. He had managed false alarms before, satellite glitches showing phantom launches, radar returns from meteors misidentified as missiles, computer processing errors generating spurious contacts. Every false alarm had been resolved within seconds through standard verification procedures. Check satellite data independently, verify with radar systems, confirm through multiple data sources. At 0247.45, 30 seconds after the first contact appeared, Krisiak's screen showed 117 missile launches. The contacts were appearing in clusters, suggesting coordinated launch from multiple Soviet submarines positioned off the Atlantic coast. The computer projection system was calculating impact points and displaying them on the tactical map. Washington, D.C., New York, Boston, Philadelphia, Norfolk. At 0248 days, 1 minute after the first contact, the count reached 183 launches. The pattern was clear. This was a coordinated Soviet submarine attack using SLBMs to strike American command centers and population centers along the East Coast. The attack profile was consistent with Soviet doctrine for surprise first strike, using submarine forces positioned close to American shores to minimize warning time. At 0248.15, the contact count stabilized at 220 launches. The displays showed 220 Soviet SLBMs inbound toward the United States. Estimated time to first impact, 16 minutes and declining. Krisiak reached for the red phone, the direct line to the National Military Command Center at the Pentagon, and the direct line to Strategic Air Command Headquarters at Offutt Air Force Base, Nebraska. His hand was steady, his voice was calm, but his mind was processing a reality that 4 years of training had prepared him for, but that he had never truly believed would occur. The Soviet Union had launched a nuclear attack against the United States. What Captain Krisiak did not know, what no one in the operations center knew, what wouldn't be discovered for another 2 minutes and 37 seconds, was that there were no Soviet missiles. The 220 launches displayed on every screen at NORAD were being generated by a single, failed, integrated circuit chip in a communications processor that connected NORAD's computer system to the early warning satellite ground stations. The chip, a Texas Instruments 74LS-181 arithmetic logic unit measuring 0.3 inches by 0.8 inches and costing approximately $2, had experienced a failure mode that caused it to insert simulated test data into the operational data stream. The test data, designed for system diagnostics, contained simulated SLBM launch scenarios. When the chip failed, it began transmitting test data as if it were real sensor data from early warning satellites. The NORAD computer system, receiving what appeared to be valid satellite detection data showing 220 SLBM launches, processed the data exactly as it was designed to process genuine attack data, calculate trajectories, predict impact points, assess threat level, display to command center personnel, and alert the National Command Authority. For the next 2 minutes and 37 seconds, NORAD would believe the United States was under nuclear attack. Strategic Air Command would activate launch procedures. The National Military Command Center would prepare to notify the President. And the world would approach nuclear war because a $2 computer chip had failed in exactly the wrong way at exactly the wrong moment. To understand how a computer chip failure nearly started World War III, one must understand the strategic environment of June 1980, the early warning systems NORAD operated, and the specific technical vulnerabilities that allowed a single chip failure to generate a convincing simulation of nuclear attack. The Cold War in June 1980 existed in a state of renewed tension after the relative calm of mid-1970s détente. The Soviet invasion of Afghanistan in December 1979 had collapsed the arms control progress of the previous decade. President Jimmy Carter had withdrawn the SALT II treaty from Senate consideration, imposed grain embargoes on the Soviet Union, and boycotted the 1980 Moscow Olympics. The U.S. military was in the midst of a modernization program designed to counter Soviet strategic advantages. The strategic nuclear balance in June 1980 slightly favored the Soviet Union in certain metrics. The Soviets deployed approximately 1,398 ICBMs, compared to America's 1,054. Soviet ICBMs carried larger warheads and had higher throw weight, the measure of total payload a missile could deliver. The Soviet submarine fleet operated 62 ballistic missile submarines, carrying approximately 950 SLBMs, comparable to America's 41 SSBNs with 656 missiles. American advantages lay in technology and accuracy. American missiles were more accurate, with circular error probable, CP measurements significantly better than Soviet systems. American submarine-launched missiles had longer range, allowing submarines to patrol from safer positions. American bomber forces were larger and more capable than Soviet long-range aviation, but the metric that mattered most in June 1980 was warning time. Soviet ICBMs launched from the Soviet Union required approximately 30 minutes to reach American targets, providing time for detection, assessment, and response. Soviet SLBMs launched from submarines off American coasts could reach targets in 10 to 15 minutes, compressing decision time dangerously. American nuclear doctrine in 1980 remained focused on launch-on-warning capability, the ability to detect enemy attack, make the decision to retaliate, and launch American forces before incoming warheads arrived and destroyed them. The doctrine required early warning systems capable of detecting launches within seconds and command systems capable of executing launch decisions within minutes. NORAD's early warning architecture in 1980 consisted of multiple overlapping sensor systems designed to provide redundant detection and reduce false alarm risk. The Defense Support Program satellites provided the first layer of detection. 5 satellites in geosynchronous orbit used infrared sensors to detect missile launches anywhere on Earth. DSP satellites could distinguish between ICBM launches, SLBM launches, and satellite launches based on infrared signature characteristics and trajectory profiles. Detection data transmitted to ground stations at Buckley Air National Guard Base in Colorado and Noongar in Australia, which processed the data and relayed it to NORAD within 60 to 90 seconds of launch detection. The ballistic missile early warning system radars at Thule, Greenland, Clear, Alaska, and Fylingdales Moor, England, provided the second detection layer. BMEWS radars could detect ICBMs at ranges exceeding 3,000 miles, providing 15 to 20 minutes of warning. The radars operated continuously, scanning approach corridors from the Soviet Union toward North America. The PAVE-PAWS radars at Beale Air Force Base, California, and Otis Air National Guard Base, Massachusetts, provided coverage of SLBM approach corridors from the Atlantic and Pacific Oceans. PAVE-PAWS was specifically designed to detect submarine-launched missiles, which followed lower, faster trajectories than ICBMs. All sensor data fed into NORAD's 427M computer system, the Philco 2000 mainframe installation that processed detection data, correlated contacts from multiple sensors, calculated trajectories, and displayed information to operations center personnel. The 427M system was the same system that had experienced the training tape incident in November 1979. Following that incident, software modifications and procedural changes had been implemented to reduce false alarm risk. But the modifications had focused on preventing training data from entering the operational system. They had not addressed the vulnerability that would cause the June 1980 incident. Hardware failures in the communication processors that connected the 427M mainframe to remote sensor sites. The communication processors were IBM 3705 systems, essentially specialized computers that manage data transmission between NORAD's mainframe and remote sensor stations. The 3705 units contained hundreds of integrated circuit chips performing various functions: data routing, error checking, format conversion, and diagnostic testing. One of the diagnostic functions involved periodic transmission of test data to verify communication links were functioning correctly. The test data consisted of simulated sensor reports representing various scenarios: ICBM launches, SLBM launches, bomber deployments, satellite passes. The test data was clearly marked with header codes identifying it as test data, ensuring the mainframe would recognize it as non-operational. But if the communication processor experienced certain types of failures, specifically failures that affected the chips responsible for inserting test data headers, the test data could be transmitted without proper identification. The mainframe, receiving data that appeared to be valid sensor reports, would process it as real. This vulnerability had been identified during system design reviews, but had been assessed as extremely unlikely. The failure would require a specific chip to fail in a specific way that corrupted header data while leaving payload data intact. The probability was calculated as less than 1 in 10 million. The risk was accepted. On June 3, 1980, at 0247 hours, the 1 in 10 million failure occurred. June 3, 1980, began routinely at NORAD. The overnight shift, running from 2200 hours on June 2nd to 0600 hours on June 3rd, was 3 hours into the duty period. The operations center was quiet. Display screens showed normal conditions. Satellite data indicated no unusual Soviet military activity. Radar systems showed routine air traffic. Nothing suggested that within minutes the United States would believe it was under the largest submarine-based nuclear attack in history. At 0247 hours, the communication processor at the DSP ground station at Buckley Air National Guard Base experienced a failure in integrated circuit chip U47, a Texas Instruments 74LS-181 arithmetic logic unit. The chip was one of thousands in the communication processor, responsible for a specific function, managing the insertion of test data headers during diagnostic operations. The chip failure was caused by electromigration, a gradual degradation of semiconductor junctions that occurs over time as electrical current flows through microscopic circuits. The chip had been in service for approximately 18 months and had processed billions of operations. On June 3rd, at U247-8, one particular junction failed, creating an open circuit that disrupted the chip's normal function. The failure mode was unusual. Instead of failing completely, which would have been detected by error checking systems, the chip failed partially. It continued functioning well enough to avoid triggering error alerts, but failed badly enough to corrupt the test data headers it was supposed to generate. At 0247.10, the communication processor initiated a routine diagnostic test, as it did every 30 minutes. The test involved transmitting simulated SLBM detection data to the mainframe to verify the communication link was functioning correctly. The test data represented a scenario of 220 Soviet SLBM launches from submarines in the Atlantic, a maximum threat scenario used for diagnostic purposes because it stressed the system with high data volume. At 0247.12, the failed chip U-47 attempted to insert the test data header, the code sequence that would identify the data as test data rather than operational data, but the chip failure corrupted the header. Instead of generating the correct test data identifier, the chip generated a header that resembled an operational data identifier. At 0247.14, the mainframe received the data from the communication processor. The data appeared to be valid DSP satellite detection reports showing SLBM launches. The header codes, though corrupted by the chip failure, matched the format of operational data closely enough that the mainframe's error-checking algorithms did not reject them. The mainframe began processing what it believed was a genuine report of 220 Soviet SLBM launches detected by DSP satellites. The processing was automatic, designed to handle attack data within seconds. Step 1. Parse detection data. Extract launch locations, launch times, missile types. Step 2. Calculate trajectories. Compute ballistic paths from launch points to predicted impact areas. Step 3. Assess threat level. Determine number of warheads, target categories, time to impact. Step 4. Generate displays. Create visual representations for Operations Center screens. Step 5. Activate alerts. Trigger audio warnings and notification systems. At 0247.14, the first contact appeared on Operations Center displays. Captain Krzysiak at Console 1 saw the red icon representing a detected SLBM launch. Within seconds, more contacts appeared as the mainframe completed processing the data stream from the failed communication processor. At 0247.30, Krzysiak's screen showed 63 contacts. He initiated verification procedures, the same protocols that had resolved previous false alarms. Console 2, verify satellite data. Are you showing launches? Console 2, monitoring DSP satellite data through an independent display system, responded, affirmative. Console 1, satellite shows multiple SLBM launches, Atlantic operating area. Count is 78 and climbing. This was the first safeguard failing. Console 2's independent display system was fed by the same communication processor that was generating the corrupted data. The independence was logical, not physical. Both displays were showing the same false data from the same failed chip. At 0247.45, with the contact count at 117, Krzysiak ordered radar verification. Pave pause NORAD command. We're showing large SLBM launch detection. Do you have radar confirmation? The Pave pause radar at Otis Air National Guard Base, Massachusetts, was monitoring the Atlantic approach corridor. The radar operator responded, NORAD command. Pave pause Otis. Negative radar contact. We're not showing any missiles inbound. Skies are clear. This was the critical verification. The radar data contradicted the satellite data. If Soviet submarines had launched 117 SLBMs from the Atlantic, pave-pause radars would detect them within 2 to 3 minutes of launch. The missiles would be on ballistic trajectories that radar could not miss. At 02:48 Zuzuk, the contact count reached 183. Krzysiak faced the assessment that would determine whether the alert escalated or was identified as false. The satellite data showed massive attack. The radar data showed nothing. Which data was correct? Training dictated, trust multiple sources over single sources. Satellite and radar should correlate. If they don't, investigate discrepancy before escalating. But training also dictated, don't delay notifications that could cost critical warning time. The balance was precarious. Krzysiak made the decision that protocol required. Notify the National Command Authority of the alert while simultaneously investigating the discrepancy. At 02:48.15, with the contact count stabilized at 220, Krzysiak reached for the red phone connecting NORAD to the National Military Command Center at the Pentagon. The call connected instantly. Navy Captain James Walters, senior duty officer at the NMCC, answered. NMCC, secure line. Krzysiak spoke with measured calm. NMCC, missile attack command. We are detecting large-scale SLBM launch, Atlantic Theater. Count is 220 missiles. Satellite confirmation. Radar shows negative at this time. We assess possible false alarm, but require NMCC awareness per standing protocols. There was a pause of perhaps 3 seconds. Then Walters responded, NORAD, NMCC copies missile attack warning. 220 SLBM contacts. Satellite detection. Radar negative. Confirm your assessment. Possible false alarm? Affirmative, NMCC. Satellite data shows launches. Radar shows clear skies. Investigating data discrepancy, but notification required per protocol given contact count. At 02:48:30, the NMCC activated initial alert procedures. Strategic Air Command received notification of possible attack. SAC headquarters at Offutt Air Force Base, Nebraska, placed bomber forces on increased alert status. B-52 bombers on ground alert were brought to immediate launch readiness. Crews boarding aircraft and starting engines. At 02:48:45, SAC Command Post Aircraft, EC-135 Airborne Command Centers launched from Offutt. The aircraft, continuously maintained on alert, were airborne within 15 minutes of notification. Their mission was to provide command and control for strategic forces if ground-based command centers were destroyed. At 02:49 Zaksha, 2 minutes after the first contacts appeared, NORAD's computer technicians identified the source of the false data. A technician monitoring communication processor diagnostics noticed that the test data transmission that had occurred at 02:47.10 corresponded exactly with the timing of the missile attack alert. The technician examined the communication processor logs and discovered that chip U-47 had failed during the test data transmission, corrupting the test data headers. The technician reported to the operations center, NORAD Command, Computer Room. We've identified the source of false data. Communication processor chip failure caused test data to be transmitted without proper headers. The 220 contacts are simulated test data from diagnostic routine. There is no attack. Repeat, no attack. This is false alarm from hardware failure. At 02:49:30, Krzysiak received confirmation from multiple sources. Pave-pause radar showed no contacts. BMEW's radars showed no contacts. Direct communication with DSP satellite ground stations, bypassing the failed communication processor, showed no detection of launches. The satellite data that had triggered the alert was confirmed as false data generated by the chip failure. At 02:50, 3 minutes after the first contact appeared, Krzyzak called the NMCC. NMCC, NORAD command. Disregard previous missile attack warning. Confirmed false alarm. Source identified as communication processor hardware failure generating test data without proper identification. No Soviet launches detected. All sensors confirm negative. I say again, false alarm, no attack. At the Pentagon, Captain Walters received the message and immediately issued stand-down orders. SAC bomber crews shut down engines and returned to ready rooms. The Airborne command post aircraft already launched continued their flights, but transitioned from alert status to routine training missions. The alert was over. Total duration from first contact to confirmed false alarm, 2 minutes and 46 seconds. But the incident was not over, because on June the 6th, 1980, 72 hours later, it happened again. June the 6th, 1980, 310 hours. The overnight shift at NORAD was different personnel than June 3rd. The operations center had been briefed on the June 3rd false alarm. Computer technicians had examined the communication processor, identified the failed chip U-47, and replaced it. System tests had been conducted. Everything appeared normal. At 031014, the first contact appeared on Operations Center displays. Contact Sierra 1, SLBM launch detected by DSP satellites, Atlantic Operating Area. Then more contacts. Within 30 seconds, the displays showed 37 SLBM launches. The duty controller, Major Robert Frost, immediately suspected false alarm. This is the same failure mode as June 3rd. Computer room, verify communication processor status. Are we receiving test data? The computer room responded, negative command. Communication processor shows normal operation. Chip U-47 was replaced after the June 3rd incident. All diagnostics show green. Data appears to be genuine sensor data. At 031045, the contact count reached 89. Major Frost ordered radar verification. Pave pause, NORAD command. Are you showing inbound contacts? Pave pause. Otis responded, NORAD command, negative. Skies are clear. No radar contacts. At 031100, the contact count stabilized at 220, the exact same number as June 3rd. The exact same scenario, 220 SLBM launches from the Atlantic. Major Frost realized immediately that this could not be coincidence. This was another false alarm, but from a different source than June 3rd. At 031115, computer technicians identified the problem. The communication processor had a backup chip, designated U-48, that performed the same function as the failed U-47. When U-47 was replaced after June 3rd, U-48 took over as the primary chip. U-48 had now failed in the same manner as U-47, using the same electromigration mechanism, corrupting test data headers in the same way. The reason both chips failed in the same manner was that they were from the same manufacturing batch, installed at the same time, experiencing the same electrical stress, degrading at similar rates. When U-47 failed on June 3rd, U-48 was already close to failure. 3 days later, U-48 reached its failure point. At 031145, less than 2 minutes after the first contact appeared, Major Frost declared false alarm based on multiple factors. Radar showed negative, contact count and scenario matched June 3rd exactly, and computer analysis indicated communication processor anomaly. The NMCC was notified of the false alarm before any bomber alert was issued. Total duration of the June 6th incident, 1 minute and 31 seconds. The fact that the same failure occurred twice within 3 days, generating the same false attack scenario both times, demonstrated a systemic vulnerability in NORAD's early warning architecture. A single component failure in the communication infrastructure could generate false alerts, convincing enough to reach the National Command Authority and trigger initial response procedures. The investigation into the June 1980 incidents was immediate and intensive. The Department of Defense, the Air Force, and congressional oversight committees demanded answers. How could a $2 computer chip generate a false alarm showing 220 Soviet missiles and convince NORAD the attack was real? What safeguards had failed? What prevented this from happening again? The technical investigation identified the failure mechanism. Chips U-47 and U-48 were Texas Instruments, 74LS-181 arithmetic logic units from manufacturing batch K793347, produced in the third quarter of 1978. The chips were installed in the communication processor in January 1979 and had operated for approximately 18 months before U-47 failed and 18 months plus 72 hours before U-48 failed. Metallurgical analysis of the failed chips revealed electromigration damage in specific circuit junctions. The damage was caused by current density exceeding long-term reliability specifications. The chips were operating within design specifications for voltage and temperature, but the specific application in the communication processor subjected certain junctions to continuous high-duty cycle operation that accelerated electromigration. The failure mode was particularly insidious because the chips did not fail completely. A complete failure would have triggered error detection systems. Instead, the chips failed partially, continuing to function well enough to avoid error detection, but failing badly enough to corrupt data processing. The investigation identified multiple safeguards that had failed to prevent the false alarm from reaching the operations center. First safeguard, test data headers. The communication processor was supposed to insert headers identifying test data. The chip failures corrupted these headers. The mainframe's header verification algorithms were not robust enough to detect the corrupted headers as invalid. Second safeguard, independent verification displays. Console 2's independent satellite data display was supposed to provide redundant verification, but both displays fed from the same communication processor, so both showed the same false data. Third safeguard, radar correlation. PAVE-PAWS and BMU's radars were supposed to confirm satellite detections. The radars worked correctly, showing no contacts, but this created an ambiguous situation. Satellite showed attack, radar showed nothing. Which was correct? Fourth safeguard, multiple sensor correlation. The mainframe was supposed to correlate data from multiple satellites and radars before generating alerts, but the system architecture allowed satellite-only data to generate alerts if the data volume was high enough, which it was for the 220 contact scenario. The investigation made multiple recommendations. Recommendation 1. Replace all chips from batch K793347. Approximately 2,400 chips from the same manufacturing batch were installed in NORAD systems. All were replaced within 30 days of the June 6th incident. Recommendation 2. Implement enhanced header verification. The mainframe software was modified to perform cryptographic verification of data headers. Test data headers would be encrypted with keys that operational systems would actively reject. Recommendation 3. Establish physical independence for verification displays. Console 2's verification display was reconfigured to receive data through a separate communication path, ensuring true independence from the primary data stream. Recommendation 4. Require multi-sensor correlation for high-confidence alerts. The mainframe software was modified to require both satellite and radar confirmation before generating alerts involving more than 10 contacts. Satellite-only alerts would be flagged as low confidence requiring immediate verification. Recommendation 5. Implement redundant chip architecture. Communication processors were redesigned to use triple modular redundancy for critical functions, where 3 chips performed the same function and results were compared. A single chip failure would be detected by mismatch with the other 2 chips. These modifications were implemented over 6 months following the June 1980 incidents. The total cost of the modifications exceeded $50 million, orders of magnitude more than the $2 cost of the chips that failed. But the broader issue revealed by the June 1980 incidents was that NORAD's early warning system, despite redundancy and sophisticated technology, remained vulnerable to single-point failures that could generate convincing false alarms. The system's complexity, with thousands of components operating continuously under time pressure, created opportunities for failures that were difficult to anticipate or prevent. The June 1980 incidents occurred 6 months after the November 1979 training tape incident. Together, these incidents demonstrated a pattern. NORAD's early warning system was generating false alarms, serious enough to reach senior leadership and trigger initial response procedures approximately twice per year. If this pattern continued, eventually a false alarm would occur under conditions where verification took longer, where ambiguity was greater, where political tensions were higher, and where the decision to retaliate was made before the false alarm was identified. The timeline of what would have occurred if the June 3rd false alarm had not been identified in 2 minutes and 46 seconds can be constructed from nuclear war planning procedures documented in declassified records. June 3, 1980, 02:48:30, hypothetical extended timeline. Major Frost at NORAD is unable to immediately verify the false alarm. PAVE pause radar is showing ambiguous returns that might or might not be consistent with SLBM launches. Computer technicians have not yet identified the chip failure. The satellite data continues showing 220 launches with high confidence. IR-249-0, the NMCC, receiving NORAD's assessment that satellite data is high confidence but radar is ambiguous, classifies the alert as possible attack requiring presidential notification. The duty officer at NMCC calls the White House Situation Room. IR-249-30, the White House Situation Room notifies National Security Advisor Zbigniew Brzezinski at his residence. Brzezinski is informed, NORAD is reporting possible SLBM attack, 220 missiles, satellite detection with ambiguous radar. Estimated time to first impact if real, 15 minutes. 0250, soon. Brzezinski, remembering the November 1979 false alarm, where he had nearly called President Carter prematurely, demands highest confidence assessment before presidential notification. He calls NMCC directly, "What is your confidence level this is real?" NMCC responds, "Sir, satellite data is definitive, 220 launches detected, but radar is not confirming. We are investigating the discrepancy. Current assessment is 60% confidence. This is genuine attack. 40% confidence false alarm." 0251, Brzezinski faces the decision he faced in November 1979. Call the president now based on ambiguous information or wait for better verification and risk losing critical decision time. This time, the situation is more ambiguous than November 1979. The satellite data is less overwhelming, 220 versus 2,200 contacts, but radar is showing possible ambiguous returns rather than clear negative. Brzezinski decides to call President Carter. "Mr. President, we have a possible nuclear attack situation. NORAD is showing 220 Soviet submarine missiles launched from the Atlantic. I need you to come to the Situation Room immediately." 0252, Sirs. President Carter is woken and briefed. He dresses rapidly and begins moving to the White House Situation Room. Travel time from residence to situation room, approximately 3 minutes. During travel, Carter receives updated briefings via secure phone. Carter arrives at the Situation Room. Present are Brzezinski, Secretary of Defense Harold Brown, Chairman of the Joint Chiefs David Jones, and senior military officers. The Situation Board shows 220 inbound contacts, estimated impact in 12 minutes. Carter asks the critical questions. What is your confidence this is real? Why isn't radar confirming? Could this be another false alarm like November? General Jones responds, Mr. President, satellite data is high confidence. Radar is ambiguous, showing possible returns that might be missiles with reduced signatures using stealth technology. This could be a real attack using new Soviet capabilities that reduce radar detectability. Or it could be false alarm. We're investigating, but time is short. 0254, go. Secretary Brown presents the options. Mr. President, if this is real and we don't launch before impact, we lose our ICBM force. If this is false alarm and we launch, we start nuclear war. You have approximately 8 minutes to decide. Carter, facing the impossible decision, asks, how confident are you this is real? Jones responds, Sir, I'm 60% confident it's real based on satellite data, but I'm 40% uncertain due to radar ambiguity. Carter, that's not good enough. We don't launch based on 60% confidence. Continue verification, but prepare forces for launch in case verification confirms attack. 0255.0, Strategic Air Command, receives orders to bring all forces to maximum alert, pre-launch status. B-52 bombers start engines. ICBM crews go to launch stations. Submarine communication stations prepare to transmit launch orders. 0256 Dururo. NORAD computer technicians identify the chip failure and confirm false alarm. The notification is transmitted to NMCC. 025630 NMCC calls the Situation Room. Mr. President, NORAD has confirmed false alarm. Communication processor, no Soviet failure. Launches. We are issuing stand-down orders now. Carter, confirmed. This is definitely false alarm. NMCC. Yes, sir. Confirmed through multiple independent checks. The chip failure has been isolated. There is no attack. 0257 ZO. Carter orders stand down. The crisis is over. But in this hypothetical timeline, the world came within 5 minutes of launch orders being issued based on a false alarm that was given 60% confidence of being real. If computer technicians had taken 3 more minutes to identify the chip failure, if Brzezinski had been more cautious about calling Carter, if Carter had decided 60% confidence was enough to order launch, the outcome would have been catastrophic. 0258. Continued hypothetical where launch is ordered. Carter concludes that 60% confidence, combined with insufficient time for further verification, requires launch. Gentlemen, we have 8 minutes to impact if this is real. We cannot wait longer. I am authorizing launch of retaliatory forces. Secretary Brown, transmit the orders. 025830. Launch orders are transmitted to Strategic Air Command, submarine communication stations, and bomber bases. The orders are authenticated using the nuclear codes in the Presidential Emergency Satchel. 0259-0. Minuteman ICBM launch crews authenticate the orders and begin launch sequence. Approximately 450 Minuteman III missiles are brought to final launch status. The 300-0 first Minuteman missiles launch from silos in Montana, Wyoming, and North Dakota. Within 90 seconds, approximately 400 missiles are in flight toward Soviet targets. 0301-0. Soviet early warning satellites detect American ICBM launches. Soviet leadership is notified. Massive American attack underway. 00330. Soviet General Secretary Leonid Brezhnev, confronted with report of American attack, orders Soviet retaliatory launch. Approximately 1,000 Soviet ICBMs begin launching. Hydro 3320. First American ICBM warheads impact Soviet targets. First, Soviet ICBM warheads impact American targets. Nuclear war is fully engaged. By 0400 hours, approximately 2,500 nuclear weapons would have detonated across North America, Europe, and the Soviet Union. Casualties would exceed 200 million in the first hour. By dawn, human civilization would be entering the collapse that would kill billions more over subsequent months. This timeline would have been triggered by a $2 chip failing in a communication processor, generating false data showing 220 Soviet missiles and creating ambiguity that delayed verification long enough that launch orders were issued before the false alarm was confirmed. The actual timeline ended at 2:50:51 when the chip failure was identified and confirmed false alarm was declared. The margin separating continued peace from nuclear war was 2 minutes and 46 seconds of verification time, and the fact that radar data clearly contradicted satellite data, providing enough confidence to delay launch orders until verification was complete. The statistics of what was prevented by 2 minutes and 46 seconds of verification procedures quantify the margin by which civilization survived on June 3, 1980. June 3, 1980. Incident summary. First contact detected 0247, 14 hours. False alarm confirmed 0250, 51 hours. Duration 2 minutes 37 seconds. False data source failed integrated circuit chip U47 in communication processor chip. Type Texas Instruments 74LS181. Arithmetic logic unit. Chip cost $2. Simulated attack 220 Soviet SLBM. Launches from Atlantic alert level reached. NMCC notified. SAC bombers on alert. Presidential notification. Not reached before false alarm confirmed margin of safety. Radar data clearly contradicted satellite data, enabling rapid verification. June 6, 1980 incident summary. First contact detected 0310, 14 hours. False alarm confirmed 0311, 45 hours. Duration 1 minute 31 seconds. False data source failed chip U48, backup to U47. Simulated attack, identical to June 3rd, 220 SLBM launches. Level reached. Alert. Identified as false alarm before NMCC, full alert verification time, faster due to recognition of similarity to June 3rd incident. If false alarm had not been identified and launch orders issued, American missiles launched, approximately 400 Minuteman III ICBMs, U-200 warheads, Soviet detection and retaliation time, 3 to 5 minutes. Soviet missiles launched, approximately 1,000 ICBMs, 5,000 plus warheads. Total weapons detonated, approximately 2,500 to 3,000 immediate casualties, 150 to 250 million first-year casualties, 500 million to 1 billion long-term effects. Nuclear winter, agricultural collapse, civilization collapse, cost of chip that failed. $2 cost of investigation and system modifications, 50+ million cost of prevented nuclear war. Incalculable margin of survival, 2 minutes 37 seconds of verification procedures, plus clear radar data contradicting false satellite data. On June 3, 1980, at 0247 14 hours, a computer chip failed inside a communication processor at NORAD. The chip, a Texas Instruments 74LS181, measuring less than 1 square inch and costing $2, failed in a way that corrupted test data headers, causing simulated attack data to be transmitted as if it were real sensor data from early warning satellites. NORAD's mainframe computer processed the false data as genuine attack information. Displays showed 220 Soviet submarine-launched ballistic missiles inbound toward the United States. The National Military Command Center was notified. Strategic Air Command bomber forces went on alert. The world moved toward nuclear war because of a failed $2 chip. For 2 minutes and 37 seconds, NORAD believed the United States was under attack. Verification procedures identified contradictions between satellite and radar data. Computer technicians discovered the chip failure. The false alarm was confirmed and stand-down orders were issued. 3 days later, on June 6th, the backup chip failed in exactly the same way, generating exactly the same false alarm, 220 Soviet missiles launching. This time, verification was faster because controllers recognized the scenario from 3 days earlier. The NORAD computer chip failed and showed 220 Soviet missiles launching, nearly starting nuclear war in June 1980. Twice within 3 days, the same failure mode generated the same convincing false alarm. And twice, verification procedures identified the false alarm before launch orders were issued. The incidents proved that NORAD's early warning system, despite sophistication and redundancy, remained vulnerable to single-point failures that could generate false alarms, convincing enough to reach the highest levels of command and trigger initial response procedures. A $2 chip failure created conditions where nuclear war was prevented only by rapid verification and clear radar data contradicting the false satellite data. The chip failed. The system believed it was real. The world approached nuclear war. And 2 minutes and 37 seconds of verification, twice in 3 days, stood between continued peace and the end of civilization. June 1980 taught the lesson that nuclear weapons on high alert, responding to early warning systems vulnerable to component failures, created unacceptable risks. The warning time that made deterrence credible also made false alarms catastrophic. And when thousands of components operated continuously under time pressure, failures were not anomalies but inevitabilities. The computer chip failed. 220 missiles appeared on displays. The system processed it as real. And only the fact that radar clearly contradicted satellite data, providing enough confidence to delay launch orders until verification was complete, prevented a $2 chip failure from starting World War III.